Well, hello, my exponential friends. Let's continue our journey as we look at exponential growth and decay. What I like about today's lesson, it's kind of like explaining why the equation looks like it does, so I do enjoy that. So the model of exponential growth and decay, it's basically the equation. So here's the basic equation right here. Y equals a times b to the x power. Now notice here x and y look differently than in a linear relationship. In a linear relationship, y equals mx plus b, or if I look at y equals my slope plus my starting point, or my initial value. So in a linear relationship, this is where my value is starting, and this is how much it's growing each time. It's like adding 2 each time. Okay. Now, so that's linear. That's going to make a nice straight line. This is different over here when you're talking about an exponential relationship because your independent variable, your x value, is an exponent. So a couple things you're looking for is your a value, which is your initial amount. That's why it says when x is 0. It's kind of where you're starting. What do you have? The reason why we say that a can't be 0 is because, really it has to start somewhere. For something to grow exponentially or decay exponentially, it really has to exist first, like the rabbit population or bacteria. You can't like have no bacteria and then it grow exponentially. You got to have at least one to get things rolling. So that's how this starts. So it's got to be at least one or larger. Okay, so that's what's happening with that, and my smartboard's going a little crazy. And then I've got my base amount. Now this is that the growth factor, as another name we call it. How much is it growing each time consistently? What's happening with that? And we can see that through multiplication. Here we saw it through adding. In this linear relationship, I would be adding 2 each time. In this exponential relationship, I would see that it's being multiplied by a certain value consistently each time. And that's what I'm looking for. So I've got my starting point, my initial value. I have my growth factor, how much it's changing by each time. So it still has all the pieces that you and I recognize, but just it's exponential. Okay, so let me look at this one. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. Okay, so it's increasing 7% each year, and that's going to be dependent on the value of the year before. So this is growing. This is growing exponentially. It's growing because it says increased, and the percent's telling me exponential. So I'm going to write down my original exponential equation. So y equals a times b to the x power, so we can get our different pieces. So we have our, right here, this is going to be our initial amount. And our initial amount was 360 billion. So I'm going to do 360 and then just keep track of that. My base amount, well, let's look at my y. My y is going to represent, in this case, the amount of money spent. So money spent. Because at the end we want to know what we actually solved for. And x in this situation, because we got to look, is this x? It usually represents like time. So is this months, is it days, is it hours? This is representing years. And then this b in this one, which is our base number and all this, how much it's changing each time. So this is my growth factor. So this is my growth factor, how much is it's changing each time. So I see that it's changing 7% each year, but you know what, I need to include the 100% of what's happening prior. So I've got 100% of the year and 7% more, so it's a total of 107% is my growth factor, but I want to use 1.07 for my number. So let me plug a few things in that I can already see. I can see that my equation is going to be y equals 360 times 1.07 to the x power. Now notice I'm going to keep my x inside the parenthesis. Actually, it really doesn't matter. It's just going to influence the 1.07. But I do need to multiply those together. All right, so now I need to come back and see what the question is, now that I have my equation about how much money will be spent, So I'm looking for y in 2015, so I need to look at the 2, and I'm not going to put in, 2015 as my exponent. It looks like it's about 10 years difference. So I'm going to solve for y equals 360 times 1.07 to the 10th. And when I do 1.07 to the 10th, times 360, I end up with about 708. And that's not $708, that's 708 billion. There you go. Wow, that's a really fun way to spell billion. It's all there, but I think I wrote billion. Maybe it's a French version of this. All right, will you go ahead and press pause and you try on B. All right, I don't see I got it on this one, so this must be one I get to do with you. I know. So if you pause it and try to work it out, man, way to go. I should buy you a brand new puppy. I just don't have any extras. So I'm going to go ahead and take care of this one with you. We know we're working with 107%, which is 1.07. That's our interest rate that we're working with here. What is an expression that represents the equivalent monthly increase? Okay, blah, 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 monthly increase. So we know that 1.07 is annual, so I really want 1/12 of that. Okay, so it's like that'll give me the monthly amount. So, and I can look at that as an exponential amount because this is an exponential change, and so that would get me like my monthly interest that's happening. That's how much it's growing. So instead of growing the year, it's growing the month. And then I need to look at my timing. And my timing, if we see as x as being the year, there's 12 months in a year. Okay, so I'm going to do 12 times however many years you tell me. So if you say 2 years here, I'm going to multiply that by 12. Okay, and this is not something that I need you to actually replicate. I just want you to try to keep an eye on, like, there's other ways exponents show up in the world around us, like for instance in this situation. So if I do some simplifying here, 107% or 1.07 to the 1/12th power ends up being 1.0057, so 12 times x power. And this is really our equation. So, and really this is telling me like a monthly rate. So I have two equations. I've got this one, and I also have a second one that I can work with if somebody gives me like the month. So if they give me 3 months, I can use this equation. If they say 7 months, I can use this equation. If they say 2 years, I'm going to take 2 times 12 and use the exponential to show the change. All right, that's just an extension kind of talking about it. But this stuff is something that you really want to pay attention to and be able to replicate. So this is talking about compound interest. Compound interest is about, I have some money in the bank, I get some interest for it. The bank saying thank you for letting us use your money and invest it. So as a thank you, I get some interest back. So they give me some money back, and then the next month I have more in my account. And then the interest is going to be calculated on the new amount. And then the next month after that, I have collected more interest, so my account now has more in it. So that's how it compounds. It just keeps building on itself. And here's the equation that works for that, right here. So I have the balance that's in my account is made up of P, the principal, which is my initial deposit. Okay, we saw that. That's like our y-intercept, our starting point. So I have a certain amount of money in there. And the 1 represents the 100%, so I'm going to be taking 100% of the money I put in. That's what I'm multiplying by. Let's look at the R. The R is the annual interest, so the yearly interest, and you want that to show up as a decimal, and it's a ratio of the number of times the interest is being compounded. So we want to pay attention. Is it annual? Is it twice a year? Is it 4 times a year? So we want to pay attention to that, or even monthly. And then T is going to be the times in years. So let's just try this out. And this is an equation you want to get real comfortable with. And this is compound interest. Suppose when your friend was born, your friend's parent deposited $2,000 in an account. Okay, so 2,000, we already can see that this is going to be my principal amount. Paying 4.5 interest. Okay, so 4.5 interest, that's the annual interest rate. This is the R. So we have the R and we have the P. Compounded quarterly. Okay, that's the N. That's going to be the number of times it's compounded per year. And quarterly tells me 4 times a year. So the number I'm going to use for that is 4. What will the balance be after 18 years? So this is going to be my T. Okay, then I know my pieces here, so these are the things I need, and I can go ahead and start building my equation from there. Okay, so the amount that we're talking about, it's going to be the principal, which is $2,000, times 1, so it's going to get that 1%, plus, so we have the rate, which was, I covered it up here with a bunch of circles. Okay, 4.5%, but I have to turn it into a decimal, so 0.045 over n, which is representing the number of times, so it's going to happen 4 times, close parenthesis, and remember my exponent's going to be n times t, so n is represented by the 4 times t, which is 18. All right, I can keep working this out, simplifying this some more, and I do end up with like 2,000, and 1 plus that ratio simplified out is like 1.0112, and that's all to the 14 times 8, which is the 72nd power. And I keep multiplying, and the balance is going to be, if I simplify all of this, the total will be like, it's like 44,000, no, $4,075.53. That's about that after 18 years. All right, I'm going to have you try it. I think we got it. Yeah, got it. All right, substitute it in, and you give it a try. Now keep in mind, this one's interesting. It says compounded monthly. Okay, so think about how many times a year that is run. Pause. All right, take a look at how you did. Yep. Substitute everything in. I noticed the monthly one is going to give me a 12. It plays out at my exponent for 18 years. I started simplifying, cleaned up inside the parenthesis, then I used the exponent. I did 2,000 times 2,000, I end up with just over $4,400 is the answer to that question. All right, the function y equals a times b to the x power, so my starting point, my initial amount, and my growth factor, how it's changing, can be modeled exponential decay as well as exponential growth. We've been talking about things growing a lot, but things can decay as well. In both cases, b is determined by the percent rate of change, okay? Really, if something's changing a certain amount, it's growing, there's a growth factor. The value b will tell you if it's growth or decay, so that's really important. This value, that growth factor, that base amount, is going to let you know if you're looking at exponential growth, it's going to go up, or exponential decay is if you have something and it is going down. We can see exponential growth happening, well, let's just exponential decay. Let's look at this. Exponential decay is where a is greater than 0. Okay, so we have like a starting point somewhere, and then where b sits in between 0 and 1. So your growth factor is in between 0 and 1. Now, if you think about it, if you have a base of 1, 1 to the 3rd power is still 1, or 1 to the 7th power is still 1. But when you start increasing it, like 1.2 to the 3rd power, 1.2 to the 3rd power is like 1.728. But you take 1.2 to the 4th power, 1.2 to the 4th power, it's jumping, where you have exponential growth happening here, but it is going up. But when you go below 1, like you're talking like 0.8, so 0.8 to the 3rd power and 0.8 to the 4th power, so 0.8 to the 3rd power is 0.512, and 0.8 to the 4th power is 0.4096. So this is going down. So the thing you're really paying attention to is determining if something is exponential growth or decay is if your base, your b value, if it is between 0 and 1, your value, your initial value is going down. If it's larger than 1, your initial value is going up. Let's take a look at it. Let's see, it's pressure, the atmospheric pressure is at sea level is about 101 kilopascals for every 1,000 meters. Increased in altitude, okay, the pressure decreases about 11.5%. What's the approximate pressure at an altitude of 3,000 meters? Okay, let's look at the different pieces we know. We know that we have our starting point. So if I want to start building my equation, I know my starting point. times, now let's look at our growth factor. Let's see, it is decreasing. Okay, that already tells me it is going to be exponential decay, about 11.5%. So I have 100% of something, and I am decreasing it by 11.5%, right? So 1 minus 11.5% is going to be, looks like about 88.5%. So I can see like this is decreasing this much. So I need to write it though as a decimal. So 88.5, that is giving me my percent, and then there's my exponent to top it off. All right, so this is how it's happening. Okay, what is the approximate pressure at an altitude of 3,000 meters? Okay, so the meters that we're indicating here is going to be my x value. So it's going to feel like we want to write 3,000 up here, but we got to keep in mind for every 1,000 increase that happens. So with the 3,000 increase, it's actually just 3 that's happening there. So I've got my equation to the third power. And if I simplify this whole thing, I'm going to end up with about like 70. And it's going to be 70 kilo, I guess you'd call it, kiloplasties. All right, why don't you give it a try? You're going to run the same equations, but for 5,000 meters. Press pause. Excellent. Just substitute it in. For the 5,000, I use the 5. Kept simplifying it all the way out. We about done. Oh yeah, we got this one. Ooh, multiple choice. Sweet. Oh wait, a few of these work. Okay, using compound interest formula, okay, and the information on page 417 about the 2 CDs. Okay, so you want to take a look at those. So you want to hop in your book and take a look at that. Select all the following that are true, and you kind of want to talk about that. So let's see what is true about these and what is not true. Okay. The compound interest formula is exponential growth. That is true. Compound interest is exponential, and it is going up. B, the compound interest, okay, it's not a decay, so it's not that one, because it's not going down. For C, for the CD from BankWest, N equals 12. That is not true. When you look at that page 417, you'll see why. The CD from the first bank, N times T is 60. That's important. Got to have both those pieces. So that is true. E, the growth decay factor for the CD from BankWest. Okay, so I'm looking at E, and that is not true, whereas F is true. So you can take a look at what's different about them. They have both the ones, they have the interest rate, they have it happening that amount of time, but the exponent is different, and F is the true one. G, and that is, G is not true. Yay! All right, I'm going to, let's see. I'm going to go sit in a big bath of barbecue sauce and see if I can make like